Which celestial body is breathing in the icy space? By Atlas. A female visitor from another star system is releasing 40 kilos of water per second into the cold vacuum. Too far from the sun to exhibit this behavior, astronomers whisper that it is acting like a living organism. But the story of this comet does not end there. It also carries mysteries like unusual cyanide-free iron in its tail, along with whispers about origins dating back billions of years, older than our solar system. Meanwhile, far from this star visitor, citizen scientists accidentally discovered the largest strange radio circles ever recorded. Aligning with Mercury and Ceres at a curious moment in the October sky, this deepens questions about a possible connection with By Atlas, and Blue Origin's October flight raised more questions than answers, even whether it actually happened. Let's explore thoroughly as we face these thought-provoking questions in our first multi-topic broadcast. Designed to keep late-night listeners updated with all the cosmic news unfolding above the sky, if these mysteries have captivated you as they have me, be sure to like and subscribe so you don't miss any updates as these events unfold in real time. Leave a comment to let me know where you're watching from, what time it is there, and whether you believe we are getting the full truth about these world-changing discoveries. And if you want to help this community grow, please share this video on X, Facebook, Reddit, or even just in your chat groups. You are the reason we can continue pursuing stories like this, so thank you for supporting us. Part 1. The Impossible Signal. Imagine this: you are drifting in the cold silence of space, more than 30 times the distance from Earth to the Sun, where sunlight is just a frozen whisper. The comet falls into hibernation. Everything is deeply asleep. And then you see it, a comet violently pouring water into space, releasing 40 kilos of liquid every second. This is not a small drop, but a flood of water gushing from a frozen rock where water should not flow. This is By Atlas, a comet from another star system that has come to our solar system, bringing laws from the backyard of another star. And those laws do not match ours at all. The first sign came from SWIFT, a space telescope designed to hunt gamma-ray bursts. SWIFT turned its ultraviolet eyes toward By Atlas in early 2025 and discovered the impossible: a bright halo of hydroxyl molecules surrounding the comet. Hydroxyl, or OH, is what you get when sunlight tears apart water molecules. It is the echo of dying water. And when you see oak, you know water was just there. SWIFT observed astonishing numbers at 3.521 astronomical units from the sun. By Atlas is releasing 1.351027 water molecules per second, equivalent to 40 kilos per second. To put it simply, this is like pouring the water volume of a small car into space every minute, at a distance where our comets are almost completely silent. Comets in our solar system do not do this. So far from the sun, they are cold, hibernating, nearly dead. Ice needs heat to sublimate, to change directly from solid to gas without melting, and there is not enough solar energy at this distance to drive that kind of activity. Our comets wait until they are much closer to the sun to awaken and start spewing gas and dust into space, but By Atlas did not get that memo. You might recall Oumuamua, the first confirmed interstellar visitor. That object was bone dry, no water, no outgassing, just a tumbling rock, speeding through our neighborhood silently. Then came Borisov, the second interstellar comet. Borisov was active, definitely, but it behaved exactly like our comets, following a predictable script, and it was boring in the best possible way. By Atlas is unlike either of those objects. It is living in a way that should not happen. It is screaming water into space where there should be silence, and the question hangs over everyone, accelerating through our neighborhood silently. Then there are two Borisov comets. The second interstellar comet definitely active, but it behaves exactly like our comets. It follows a predictable script and is boring in the best possible way. Unlike both of those objects, it is alive in a way it shouldn't be. It is screaming water into space where there should be silence, and the question hangs overhead. All astronomers have pointed their telescopes at this object. Simply how? What mechanism could drive this? Could it be some kind of strange ice we don't know about, sublimating at temperatures we think are too cold? Could the inside of the comet still be warm from its birth billions of years ago? Is it rotating in some strange way, focusing sunlight onto hidden reservoirs of volatile material? Or is there some chemical reaction happening inside the rock we have never encountered before? Water is just the beginning. The interstellar comet is also leaking other things: cyanide, nickel, carbon dioxide at unreasonable concentrations. Each new observation adds a layer of mystery. Each absorption line appearing in the data is another question mark. This is not just a comet behaving strangely. This is a comet seemingly operating under a completely different set of physical rules. Rules written in another star system, under different conditions with different chemistry. And now it is here in our solar system giving us a front row seat to witness processes we have never seen before. What keeps astronomers awake at night is this: if BAI Atlas is doing things that our comets cannot do, what does that say about where it came from? What star system builds comets like this? What were the conditions in that protoplanetary disk billions of years ago? And the most thought-provoking question is whether this comet is simply strange or if it is a messenger, bringing news about the diversity of the universe. Every telescope capable of seeing this object is now pointed at it, including spectrographs, polarimeters, every tool we have, because BAI Atlas is not just a curiosity, it is a window, a crack in our understanding. And through that crack, we can glimpse something extraordinary. Part 2. No iron. Comets are thought to follow certain patterns. When they get hot enough, metals start to sublimate from their surfaces, and iron and nickel appear together, like old friends always going together. You see one, you see the other. That is one of the cosmic constants we are used to relying on. Except BAI Atlas did not read the textbook. A very large telescope in Chile aimed its spectrograph at BAI Atlas and found something unreasonable. That nickel emission lines are blazing strongly in the spectrum, unmistakable, impossible to ignore, while iron is either absent or so weak it is barely detected. Nickel without iron. This is like finding smoke without fire, like finding footprints without feet. In our solar system, this does not happen when a comet heats up enough to release metals. Iron and nickel appear in predictable ratios, because they are locked together in the same mineral structure. They form together in similar processes. They sublimate at similar temperatures. They chemically bond in ways that keep them together. But BAI Atlas seems to have formed somewhere following different rules. About 2.8 astronomical units from the Sun. Astronomers measured nickel streaming from the comet at about 5 grams per second. 5 grams may not sound like much until you realize that is happening continuously, second after second, while iron is nowhere to be found. This is not a glitch, it is a pattern. The comet is telling us something fundamental about its composition. Some explanations have been proposed, and none are simple. The first possibility is chemical segregation. Perhaps, in the environment where BAI Atlas formed nickel was incorporated into volatile compounds that evaporate easily, while iron was locked into refractory minerals needing much higher temperatures to sublimate. Imagine nickel accompanying volatile ices, while iron remains trapped in rocky grains. This could create the separation we are seeing. Another idea involves organic metal compounds. On Earth, we have molecules like nickel carbonyl, where nickel atoms bond with carbon monoxide, and these compounds are volatile. They evaporate at relatively low temperatures. If BAI Atlas formed in an environment rich in carbon monoxide and other organics, perhaps nickel was trapped in these molecules. When sunlight hits them, they break down, releasing atomic nickel into the comet's coma, while iron remains locked in solid grains. Then there is space weathering. Cosmic rays and ultraviolet radiation bombarding interstellar objects for millions or billions of years. Such prolonged exposure can alter surface chemistry in strange ways. Perhaps radiation creates nickel-rich surface layers while iron is buried or chemically altered. Maybe the nickel we see is a skin, a radiation-damaged crust that does not reflect the comet's true bulk composition. Or perhaps, and this is the most exciting possibility, BAI Atlas formed in a star system with truly different elemental ratios. Not all stars. All have the same chemical composition. Older stars than stars from different parts of the galaxy. Stars formed from enriched gas clouds. By different types of supernovae. All of them have slightly different formulas. Perhaps. Atlas came from a place where nickel is more abundant than iron. In our neighborhood, perhaps, its parent star has a strange chemical composition, and that strangeness is now recorded in every molecule of this comet star. But we have to be careful here. Spectroscopy is very difficult. Detecting faint emission lines against a bright background is very complicated. There are detection thresholds. Maybe iron is there, just below the detection limit. Maybe iron emission is mixed with other spectral features. Maybe we are looking at the wrong wavelengths when the comet star approaches the sun and heats up. More iron may start to appear. That would be a reassurance. In a way, it would mean the universe still makes sense. But if that doesn't happen, what will happen if Atlas flies all the way to perihelion? The closest point to the sun and iron never appears. What will happen if the nickel-to-iron ratio remains completely reversed compared to everything we've ever seen? That would be revolutionary. That would tell us that planetary systems can create comets with metal chemistry so different that our models need a complete overhaul. This is why astronomers are obsessively observing BA Atlas. Every observation is a test. Every spectrum is an opportunity to confirm our understanding or shatter it, and currently, BA Atlas is breaking more than confirming part. BA, a comet. Star flips a switch. Comets are thought to brighten as they approach the sun. Very simple physics. More sunlight, more heating, more sublimation, more gas and dust. The relationship should be smooth, predictable, almost boring. Atlas seems never to have gotten that memo. Observers. Tracking Atlas noticed something strange about its color. Initially, the comet looked relatively neutral, maybe slightly red, typical of icy objects far away. But as it moved closer to the sun, it started to turn blue. Not a subtle change, but a vivid blue. Eerily unmistakable in photos that blue comes from two sources, cyanide molecules and atomic nickel. Both strongly emit in the blue part of the spectrum, and both start to increase sharply as the comet warms. The brightness increase is not linear, it's not smooth, it's superlinear, meaning emission lines are strengthening faster than simple geometric predictions. When you have the distance to the sun, you get 4 times the sunlight per square meter. That's the inverse square law, basic physics. But Atlas's emission is increasing even faster. Something is being unlocked. A new process is starting. Astronomers call this behavior a switch flip. Imagine a temperature threshold below which a specific ice remains solid, locked dormant. Then the comet crosses that threshold, and suddenly that ice starts sublimating gas. Production spikes. New emission lines appear in the spectrum. It's like flipping a switch. One moment the process is off. The next moment it's on, and once on it can run itself, if there's enough material to feed it. Atlas seems to have many switches. Water switches on first as far out as 3.5 astronomical units. This was already unusual then. Cyanide and nickel flare up blue as the comet warms further. Each emission indicates a different volatile reservoir being tapped, a different chemical environment reaching its activation threshold. One model that can explain this involves expanding ice grains in the comet's head rather than all activity happening at the nucleus surface. Imagine small ice grains lifted off the nucleus by escaping gas. These grains drift away from the comet, still cold, still frozen. But as they drift, they receive more and more sunlight. Eventually, each grain reaches its own individual threshold and starts sublimating. This creates a dispersed gas source not just from the nucleus but from a cloud of ice grains surrounding it. This can explain the superlinear brightness increase and sudden appearance of new emission lines. Another possibility is thermal fracturing. Comets are dirty snowballs, mixtures of ice and rock. When one part heats and expands, while another remains cold and contracts, stress builds up. Eventually, something cracks. When ice cracks, it can expose fresh material previously insulated. Suddenly, you have new surface area sublimating, new volatiles escaping. Comets undergo an outburst. BA Atlas may be cracking open as it heats up, revealing layers of frozen chemistry followed by exotic ices. Water ice sublimates at one temperature. Carbon monoxide ice sublimates at a much lower temperature. Carbon dioxide lies somewhere in between if Comet Alaska is layered like an onion, with different ices at different depths or in different regions. As it warms up, you will see a sequence of activations starting with supervolatile substances, then common volatiles, and finally the really stubborn materials, each layer peeling off like chapters in a book. This is not entirely unfamiliar to us. We have seen comets in our solar system do strange things. Some comets have sudden outbursts, brightening by 10 times or more overnight. Some comets break apart as they approach the sun. thermal stress overwhelming their structural integrity. Some distant comets remain dormant until very close to perihelion and then erupt into activity. But BA Atlas is doing this on a schedule that does not match our experience. It is active at distances where it should be dormant. It is flipping switches in ways that almost seem deliberate, and the stress is increasing as Comet Atlas continues its journey inward. Will more switches be flipped? Will we see new emission lines appear? New molecules we did not expect? Will the activity plateau or continue to accelerate, delivering new data each week? Recent surprises show this is not a stable, predictable comet. This is a play unfolding in real time. Part 4. Where does it come from? Every object in space carries a story written in its orbit, where it is going, telling you where it has been, and Comet Atlas's orbit tells a story spanning billions of years and thousands of light years. The orbit is hyperbolic, a technical term for an open curve, a path that does not repeat. BAY Atlas comes from interstellar space, orbits the Sun, and will leave again, never returning. An eccentricity greater than 1 means this comet is unbound, a free agent, a wanderer just passing through. Astronomers have traced its path backward using recovery images. Recovery is when you search old survey data to find images of an object before anyone knew it was interesting. Comet Atlas has been photographed many times by automated surveys. Some images go back when the comet was 6.4 astronomical units away, still inbound, cold and distant. By stitching these observations together, astronomers have reconstructed its orbit with increasing precision, and that orbit just grazes outside the galaxy's return path, but not just anywhere. The orbital model combined with data from the Gaia Space Telescope, which has mapped the position and motion of billions of stars, allows astronomers to make informed guesses about where Comet Atlas might originate. The answer is surprising. Galaxies have structure. Stars are not distributed randomly. Most stars, including our Sun, live in the thin disk, a relatively flat plane of younger, metal-rich stars orbiting the galactic center. But there is also a thick disk, a population of older stars orbiting on more inclined, eccentric paths. These thick disk stars are puffed up vertically, spread farther above and below the galactic plane, and chemically distinct. They are older, formed earlier in the galaxy's history, when fewer heavy elements were around. The orbit of Comet Atlas suggests it may come from the thick disk. If that is true, if this comet formed in that ancient population, it could be older than our solar system. Our solar system is 4.6 billion years old. Thick disk stars can be 7 billion years old or more. That means Comet Atlas could carry ices and rocks from a time before the Sun even existed. Think about the chemical implications of that. The gas cloud that collapsed to form a thick disk star 7 billion years ago had fewer heavy elements than the cloud that formed our Sun. Supernova explosions enriched the galaxy over time, seeding it with elements heavier than helium. The earliest generations of stars had almost only hydrogen and helium. Stars like our Sun have a few percent of heavy elements mixed in. Thick disk stars are intermediate. They have some heavy elements, but less than us. If Comet Atlas formed in that environment, its composition would reflect that lower metallicity, with less iron, less magnesium, less silicon, all the elements that build rocky planets, but it would still have plenty of volatiles. Carbon, nitrogen, oxygen, locked in ice and molecules. Perhaps that is why we see such a high carbon dioxide ratio on the water. Perhaps that is why the metal ratio looks strange. Maybe this comet is a chemical fossil from a time when the galaxy was younger and the periodic table was emptier. Of course, we cannot be sure. Tracking an object back through billions of years of galactic motion is difficult. Gravitational perturbations from passing stars, interactions with galactic spiral arms, all of that disturbs the trail. But the possibility that BAY Atlas is older than our solar system is extraordinary. We may be looking at a relic, a surviving object, a time capsule from an ancient galaxy. And if we can identify its parent star cluster, the group of stars formed together from the same gas cloud, we might one day identify its siblings, other cometary stars, perhaps even planets ejected from the same system, now scattered throughout the galaxy. By Atlas may be a letter and a message written across thousands of light years, and we are only beginning to learn how to read it. Part 5. What is accompanying it? Cometary stars are not just ice and rock. They are cargo ships carrying molecular cargo from the environment. where they were born and By Atlas is carrying some very strange goods. We talked about 40 kilos of water on paper, streaming into space at distances where water should not flow that, or rather the remaining fragments of Hiroshima when sunlight tears it apart, is the first clue showing this comet is unusual. But water is just the beginning of the story. Carbon dioxide is the real shock. Observations show that By Atlas has an extremely high carbon dioxide to water ratio. In the comets of our solar system, water usually dominates it. Is the main volatile the main driver of activity? Carbon dioxide is there, of course, but only as a supporting player. By Atlas reverses that scenario. Some measurements show 95% of volatile emissions are carbon dioxide with water, as the minority component that is the opposite, that is reversed. That is not like what we see at home in the solar system. A comet so rich in carbon dioxide, one possibility is the formation temperature with carbon dioxide condensing at a higher temperature than water ice. If By Atlas formed in a warmer region of the protoplanetary disk closer to its parent star, it may have favored incorporating carbon dioxide, while losing some water, or perhaps the radiation environment of its parent star processed the ice in ways our sun does not, or perhaps giant planets in that system. If any migrated differently, stirred the disk, and mixed material in unexpected ways, then cyanide. Cyanide, or CN, is common in comets. It is the molecule that creates the blue color for many comets, but in By Atlas cyanide appears after water, later in the comet's warming. In our comets, cyanide and water tend to appear together because they have similar sublimation temperatures. The delayed appearance of cyanide in By Atlas suggests it may be isolated differently, perhaps trapped in organic molecules needing more energy to break down, perhaps frozen in layers beneath water ice. And of course there is nickel. Nickel atoms, glowing blue, separated from their usual partner iron. We have explored that mystery, but the important point again is every element. Every molecule we detect is a clue. Volatiles tell us about temperature and pressure. During formation, refractory materials tell us about condensation sequences and thermal processing. Gas-to-dust ratios tell us about the structure of the comet and its fragility. Now, let's talk about the most obvious issue. The panspermia hypothesis. The idea that life, or at least the building blocks of life, can spread through space on comets and asteroids. By Atlas has water organic compounds, cyanide, an important precursor in prebiotic chemistry, if you wanted to design a comet to seed. A planet, chemically interesting, you would include exactly these components, but we must be very clear. This is speculation. There is no evidence that By Atlas is carrying life. No evidence that any comet has ever carried life. The panspermia hypothesis is appealing, plausible in principle, but unproven and has serious problems. Cosmic radiation is very harsh. Over millions of years in interstellar space, high-energy particles tear apart complex molecules. Ultraviolet light from stars does the same DNA proteins. Even simple amino acids can be destroyed. So, for life to survive a journey to a comet, it would need to be buried deep inside the comet, shielded by meters of ice and rock. But complex molecules that can survive are not living organisms, but chemical fossils. Molecules synthesized in the parent system of the comet, perhaps in the atmosphere of a planet, or on its surface, and then incorporated into the comet. Those molecules can survive the journey if they are stable enough and well protected, and if we can analyze them. They can tell us things we cannot learn in any other way. They can reveal the atmospheric chemistry of an alien world. They can show us metabolic pathways from an extinct biosphere. They can be messages written in carbon, nitrogen, and oxygen waiting for AI to decode them. This is why some scientists dream of intercepting one of these interstellar visitors, not just observing it from Earth, but sending a spacecraft to match its velocity to land on it, to drill into it, to take samples and analyze them. The technological challenge is huge. Interstellar objects move at speeds of tens of km per second. Catching up to one requires a spacecraft already in position, or with extraordinary acceleration capability. But the scientific benefits would be priceless. A specimen from another star system. Chemistry from another corner of the galaxy. Answers to questions we have barely learned how to ask. The Atlas comet is billions of kilometers away from the inner solar system. This time, we did not catch it, but it is showing us what is possible. It is showing us what is out there, and it is making us crave more. Part 6. Citizen Scientists Catching Ghosts. Sometimes the most important discoveries happen because someone is looking at data in a completely right way, not by algorithm, not by machine learning, but by human eyes and intuition, and sometimes that person is not a professional astronomer at all. Let me tell you about the strange radio circles. High Oracy. If you have never heard of them, you are not alone. They were only discovered in 2019, which in astronomical terms makes them almost completely new. Orices are large circular structures only visible in radio wavelengths. You cannot see them in optical light. You cannot see them in infrared. But point a radio telescope at the right part of the sky and they are there. Perfect radio emission rings, sometimes hundreds of thousands of light years wide. Floating in space like cosmic smoke rings. No one knows what they are. Leading theories involve galactic winds or shock waves from supermassive black holes, but honestly, we are still figuring them out. They are truly mysterious and finding them is difficult because they are faint, and they blend into the radio background. Automatic detection algorithms tend to miss them because they are trained to find point sources or compact objects, not large diffuse rings. Welcome to Radio Galaxy Zoo. Here is a citizen science project where volunteers visually inspect continuous radio maps looking for anomalies. They are not looking for anything specific. They are looking for weirdness. And in March 2025, a volunteer flagged something extraordinary. An object cataloged as RJG1BA1 BAB 131346910, playing 100,000 321, an easy-to-remember name. But what it is much more interesting. It is a pair of intersecting radio rings. Two circles superimposed on the sky creating a figure-8 pattern. It is the farthest and strongest ORC detected so far, and it was found not by an algorithm, not by a professional survey, but by someone volunteering their time to stare at data. This discovery was made using continuous low-frequency maps from LOFAR, a network of radio telescopes spread across Europe. LOFAR generates a huge amount of data, too much for professional astronomers to check by hand. Automated pipelines process most of it, flagging candidate objects based on brightness, shape, and other parameters. But those pipelines have filters. They have thresholds. They are designed to catch what is expected, not what is unexpected. This is where human pattern recognition becomes invaluable. Our brains are very good at detecting things that don't belong, at seeing structure in noise, at flagging something interesting even when we cannot articulate it. At Star Volunteer found Razi, 1BA1BA4690. Need to know the physics of ORCs. They just need to look at the image and think it's strange. And they were right, but it's not just that object. Ray at home has flagged many anomalies. Another volunteer found a giant radio galaxy with a strange ring structure around it. Another found a ring at the end of a jet stream, a feature that theoretical models did not predict. These are objects that were naturally lost in the flood of data. If humans do not search, there is a lesson here extending beyond radio astronomy. We are entering the era of data deluge. The Vera Rubin Observatory, when operational, will generate 15 terabytes of data every night, 15 TUP every night for 15. No group of people can review all of that. No algorithm set can catch every anomaly. We need both. We need machines to handle the large volume and humans to catch the strange cases that don't fit any existing pattern. Now, let's connect this back to by Atlas. Could a citizen scientist have flagged its anomalies early? Could that AI looking at spectral data have noticed the nigger signature without iron before professional astronomers did? Could that AI tracking Comet SAO activity have said, wait, at SAO, this object is active so far from the sun, maybe, maybe not. But the point is, anomalies like by Atlas benefit from having as many eyes as possible on the data. Professional astronomers have expertise, have training, have context, but they also have expectations, have models. They are trying to confirm, have limited time. Amateur and citizen scientists come with fresh eyes. They are not limited by what is supposed to happen. They are free to see what is really happening. There are stories about amateur astronomers discovering supernova, finding asteroids, tracking variable stars. Japanese amateur astronomer. The eccentric Itagaki has discovered many comets and a supernova. British amateur astronomer Andrew Gray co-discovered an unusual starburst. These are not coincidences. They are examples of what happens when enthusiasts with telescopes or access and data decide to look closely at the universe in the future, when telescopes flood us with petabytes of data. Citizen scientists could become the first responders to cosmic oddities, or could be the ones flagging the next comet, SAO, the next strange radio structure, next thing. Next thing makes no sense, and when they do so, professional astronomers will follow up, will investigate, will discover physics. It is a collaboration, and like all good partnerships, it is stronger than any component standing alone. Part 7. Citizen, science, and professional oversight, however, let's not pretend this is all smooth cooperation. Tension still exists. A real tension because opening the gates to citizen science means dealing with false positives with well-meaning amateurs. But flagging things that turn out to be data errors or noise, professional astronomers understandably worry about this, especially when dealing with conspiracy theorists who see alien signals in every data glitch. The Royal Astronomical Society, along with other professional bodies, has debated this widely. On one hand, citizen science helps reduce backlog, allows projects to process more data than otherwise possible, while engaging the public and creating passion for science. On the other hand, quality control is essential, because a discovery is not a discovery until it is verified, cross-checked, and peer-reviewed, and that takes time along with deep expertise. While false positives are a real problem when someone flags an object as unusual, astronomers may spend days or weeks following up, only to determine it is instrument noise, satellite trails, or cosmic ray hits. That is time that could be spent on genuine discoveries, and when false positives pile up, astronomers become skeptical of citizen reports. Then the signal-to-noise ratio drops, and fatigue sets in. Then comes the problem of confirmation bias. When people look for something specific, they tend to find it even if it does not exist. This also happens with experts, but training along with peer review helps provide checks, while amateurs may not have those checks. They may see a pattern in random data and convince themselves it is real. This is how we have claims about alien megastructures around Tabby stars, or hidden messages in the residual time of sung post. A star's calibration and amplitude error is another issue. Professional astronomers know how to assess measurement uncertainty. They know when a signal is statistically significant and when it is just noise. Amateurs may not know they can report a discovery that is actually just a fluctuation of a random variable, meaningless in the grand statistical scheme. And there is also the issue of bandwidth. If a citizen science project becomes too popular, if too many people start flagging too many things, professional astronomers responsible for follow-up can become overwhelmed. They cannot investigate everything. They have to prioritize, and that means some genuine discoveries may be missed simply because they are buried in the data pile. But the problem is, these challenges are not insurmountable. They are challenges, not absolute barriers. Training procedures can help. If citizen scientists are taught how to assess data quality, how to recognize image errors, how to estimate uncertainty, false positive rates will decrease. Mentoring programs where experienced amateurs guide newcomers can maintain standards validation by level, where multiple independent volunteers must flag the same object before it is passed to follow-up experts, can filter out false discoveries, and the opportunity is immense. Mobilizing the community to hunt anomalies means you can search larger data sets more thoroughly. Cross-checking by many independent eyes reduces the chance that an anomaly is actually missed. Just because one person had an off day, diverse perspectives mean people with different backgrounds can notice patterns that experts overlook. Let's return to the BAE Atlas comet star. Can a citizen astronomer flag its anomalies early? No, spectral data is public. Any AI with suitable software can download and view it, but spectroscopy is very difficult. It requires understanding how to identify spectral lines, calibrate wavelength, assess signal-to-noise ratio. That is not something you can do casually. But perhaps with training, with guidance, with a community working together, that AI might have noticed the anomaly before it became a headline. The same applies to the light curve generation rate. BAI Atlas comet star. Brightness over time is often contributed by amateur astronomers. If those amateurs have viewed ultraviolet data from the Swift satellite, and if they are trained to recognize unusual activity patterns, they might have flagged the superlinear brightness increase of the BAI Atlas comet star. They might have said, "This does not look like a normal comet star." Before professional surveys confirmed it, past citizen-led discoveries have proven this effective method of exoplanet transit, where you detect planets by observing small dips in the brightness of a star as the planet passes in front. It has been driven by citizen scientists analyzing data from the Kepler telescope. Projects like Planet Hunters have discovered many confirmed exoplanets. Amateur asteroid hunters have found near-Earth objects that professional surveys missed. New comet hunters. Amateur novae often outperform experts in detecting star outbursts because they observe every night with small telescopes, while professional telescopes are scheduled months in advance. Conclusion is not that we should replace professional astronomers. With amateurs, that is absurd. Conclusion is we need both. We need experts for deep expertise, theoretical frameworks, and rigorous validation, and we need citizen scientists for breadth coverage, fresh perspectives, and a huge number of eyes. This is not a competition. This is a partnership, and in the data flood era, it is a necessary partnership. Part 8. The coincidence effect, 10-2025, brought an anomaly that is excellent observing conditions for both Mercury stars and asteroid Ceres Mercury stars together, moving into a favorable optimal opposition period, bright and high above the horizon after sunset. Ceres, the largest object in the asteroid belt, moving into a favorable opposition period, bright and high above the horizon after sunset. Ceres, the largest object in the asteroid belt, reaches opposition, meaning it is directly opposite the sun in the sky, at its brightest and closest to Earth. On social media, people start connecting events. Mercury shows, Ceres shows, and now the interstellar comet is active. Is there a connection? Is some cosmic alignment happening? No. Is the gravitational field of the solar system somehow triggering or amplifying comet activity? No. To be clear, the answer is no. There is no connection. Mercury's orbit has nothing to do with the outgassing of a comet, nor does the position of Ceres relative to Earth. There is no effect on the chemistry happening billions of kilometers away. These are independent, coincidental events that can be seen simultaneously. Nothing more, nothing less. But humans like patterns. We are programmed to find them. It is a survival trait from our ancestors who noticed that some berries caused illness, and some animal tracks led to prey, making those who noticed patterns more likely to survive than those who did not. Therefore, our brains are extremely sensitive to patterns, sometimes to the point of finding them where they do not exist. This is the phenomenon of pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds, hearing voices in static noise. It is the misperception of pattern detection, and it happens with celestial events all the time. Ancient cultures saw omens in planetary alignments. When a comet appeared during a battle, it meant the gods were angry. When planets gathered in one part of the sky, it signaled the birth or death of kings. The year 1910 provides a perfect historical analogy. That was the year Comet Hale-Bopp returned, sweeping through the inner solar system on its 7.6-year orbit, and people were terrified. Astronomers discovered cyanogen. Cyanogen, a toxic gas in the comet's tail. Newspapers ran sensational headlines the comet's poisonous tail would pass Earth. People bought gas masks. Some sealed their windows, and there were even reports of suicides by those who believed the comet would kill them. Of course, nothing happened. The comet's tail is extremely diffuse, basically a near-perfect vacuum by Earth standards. The amount of cyanogen actually reaching Earth was negligible, undetectable. Comets do not pose a threat. But the coincidence of a comet appearing, alongside unrelated events, solar activity, political instability, earthquakes fueled panic as people connected dots that should not be connected. We are seeing the same thing now with Comet by Atlas. This comet is genuinely strange and unusual. Mercury and Ceres coincidentally appear at the same time, and suddenly people are building stories. Perhaps the comet is being awakened by some resonance in the solar system. Maybe its orbit is being subtly altered by gravitational disturbances. Maybe all of this is part of a bigger pattern we do not yet understand. Astronomers have run the numbers. The gravitational influence of Mercury on an object in the outer solar system is basically zero. Mercury is very small, only slightly larger than our moon and very far away. Ceres is even smaller and has less influence. The combined gravity of all the planets in the solar system cannot significantly change the orbit of By Atlas at the distances we observe it. The comet is doing what it does because of internal processes, solar radiation, and its own composition. Not because of Mercury's position in its orbit, but truth is not always important when stories are compelling. The human brain craves stories. We want events to be connected because unconnected events feel random, chaotic, and meaningless. If comet activity were linked to planetary positions, there would be order, predictability, and meaning. If they are unrelated, then we live in a universe where strange things sometimes just happen, and that is psychologically unsettling. Confirmation bias amplifies this effect. Once you start looking for connections, you find them everywhere. Mercury also appeared in a previous comet discovery. Ceres was near opposition when another unusual object was discovered. No need to worry that Mercury appears several times a year and Ceres reaches opposition annually. No need to worry that unusual astronomical discoveries happen all the time. The brain filters out non-coincidences and only remembers what fits the story. Social media exponentially amplifies this. In the past, if you had a theory about planetary alignments affecting comets, you could tell your friends who would probably tell you it was nonsense, and that would be the end of it. Now you post your theory online and immediately find a community of people who think the same way you do, sharing links, images, charts showing alignments. That AI adds new evidence. Others share it further. Soon you have a complete alternative story competing with the scientific explanation. The lesson here is not that people are stupid or gullible. The lesson is the strong coincidence, and our brains are not well calibrated to statistically refute them. With thousands of astronomical events happening all the time, some will coincide purely by chance, and those coincidences will feel meaningful even if they are not. This is important because it affects how people interpret anomalies like Comet By Atlas. If you are primed to see cosmic conspiracies, to believe that alignments are important, the strange behavior of the comet becomes evidence of something bigger. Maybe it is not a natural comet at all. Maybe it is artificial. Maybe it is reacting to signals from planets. Maybe it is part of some great cosmic mechanism we do not understand. And that brings us to an even stranger chapter in this story: the machinery of hoaxes and conspiracy theories, and how humans turn scientific mysteries into cultural myths. Part 7, Citizen Science and Expert Control. However, let's not pretend that this is all smooth cooperation. Tensions still exist. A real tension, because opening the gate for citizen science means dealing with false positives from well-meaning amateurs who flag things that turn out to be just data errors or noise. Professional astronomers understandably worry about this, especially when dealing with conspiracy theorists who see alien signals in every data glitch. The Royal Astronomical Society and other professional bodies have widely debated this issue. On one hand, citizen science helps reduce backlog, allowing projects to process more data than possible otherwise, while engaging the public and creating passion for science. On the other hand, quality control is crucial because a discovery is not a discovery until it is verified, cross-checked, and peer-reviewed. And that requires time and deep expertise, while false positives are a real problem. When someone flags an object as unusual, astronomers may spend days or weeks tracking it, only to determine it is instrument noise, satellite trails, or cosmic ray hits. That time could be spent on genuine discoveries, and when false positives pile up, astronomers become skeptical of citizen reports. Then the signal-to-noise ratio drops and fatigue sets in. Then there is confirmation bias. When people look for something specific, they tend to find it even if it does not exist. This also happens with experts, but training combined with peer review provides checks. Amateurs may lack those checks, may see patterns in random data and convince themselves it is real. This is how we get claims of alien megastructures around Tabby's star, or hidden messages in the residual timing of Samsung Porsche calibration, and amplitude errors are another issue. Professional astronomers know how to assess measurement uncertainty. They know when a signal is statistically significant and when it is just noise. Amateurs may not know and may report a finding that is actually just meaningless random fluctuations in the grand statistical scheme. And there is also the bandwidth problem if a citizen science project becomes too popular, if too many people start flagging too many things. Professional astronomers responsible for follow-up can be overwhelmed. They cannot investigate everything and must prioritize. And that means some genuine discoveries may be missed simply because they are buried in the data pile. But the problem is, these challenges are not insurmountable. They are challenges, not absolute barriers. Training procedures can help if citizen scientists are taught how to assess data quality, how to recognize artifacts, how to estimate uncertainty. False positive rates will decrease. Mentoring programs where experienced amateurs guide newcomers can maintain standards. Validation by consensus, where multiple independent volunteers must flag the same object before it is passed on for expert follow-up. It is possible to filter out fake discoveries, and the opportunity is enormous. Mobilizing the community to hunt for anomalies means you can search larger data sets more thoroughly. Cross-checking by many independent eyes reduces the chance that a real anomaly is missed just because one person had an unproductive day. Diverse perspectives mean people with different backgrounds can notice patterns that experts overlook. Let's return to the comet star by Atlas. Can a citizen astronomer flag its anomaly early? Spectral data is public. Any AI with the right software can download and view it. But spectroscopy is very difficult. It requires understanding how to identify spectral lines, calibrate wavelengths, and assess signal-to-noise ratio. It's not something you can do casually, but perhaps with training, guidance, and a community working together, that AI could have noticed the oddity before it became a headline. The same applies to the light curve generation rate of the comet star, measuring brightness over time, often contributed by amateur astronomers. If those amateurs had viewed ultraviolet data from the Swift satellite, and if they were trained to recognize unusual activity patterns, they might have flagged the superlinear brightness increase of the comet star By Atlas. They might have said, "This doesn't look like a normal comet star," before professional surveys confirmed it. Citizen-led discoveries in the past have proven this effective. The exoplanet transit method, where you detect planets by observing small dips in a star's brightness. When a planet passes in front, was driven by citizen scientists analyzing data from the Kepler telescope. Projects like Planet Hunters have discovered many confirmed exoplanets. Amateur asteroid hunters have found near-Earth objects that professional surveys missed. Amateur nova hunters often outperform experts in detecting stellar outbursts because they observe every night with small telescopes, while professional telescopes are scheduled months in advance. The conclusion is not that we should replace professional astronomers with amateurs. That would be absurd. The conclusion is we need both. We need experts for deep expertise, theoretical frameworks, and rigorous validation. And we need citizen scientists for broad coverage, fresh perspectives, and a huge number of eyes. This is not a competition. This is a partnership. And in the era of data floods, it is a necessary partnership. Part 8. The 10-20-25 conjunction effect brought an anomaly excellent observing conditions for both Mercury and the asteroid Ceres. Mercury, comet star, moving into a favorable opposition at dusk, bright and high above the horizon after sunset. Ceres, the largest object in the asteroid belt, reaches opposition, meaning it is directly opposite the Sun in the sky at its brightest and closest to Earth. On social media, people began connecting the event's Mercury star display, CRS display, and now the active By Atlas comet star. Are they related? Is some cosmic alignment happening? Is the gravitational pull of the solar system somehow triggering or amplifying the comet star activity? No. To be clear, the answer is no. There is no connection. Mercury's orbit is unrelated to the outgassing of a comet star. Ceres' position relative to Earth has no effect on the chemistry happening billions of kilometers away. These are independent coincidental events visible at the same time. Nothing more, nothing less. But humans like patterns. We are programmed to find them. It is a survival trait. Our ancestors who noticed that some berries cause illness and some animal tracks lead to prey were more likely to survive than those who did not notice patterns. So our brains are extremely sensitive to patterns, sometimes to the point of finding them where they do not exist. This is the phenomenon of pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds. Hearing voices in static, it is biased pattern detection, and it happens with celestial events all the time. Ancient cultures saw omens in the alignment of planets when a comet appeared in a battle. It meant the gods were angry when planets gathered in one part of the sky. It signals the birth or death of kings in 1910, providing a perfect historical analogy that is the year the Halley Comet returned, sweeping through the inner solar system on its 76-year orbit. And everyone was terrified. Astronomers discovered cyanogen, a toxic gas, in the comet's tail. Newspapers ran sensational headlines about the comet's poisonous tail passing by Earth. People bought gas masks. Some sealed their windows. There were even reports of suicides by those who believed the comet would kill them. Of course, nothing happened. The comet's tail was extremely diffuse, essentially a near-perfect vacuum by ground standards, and the amount of cyanogen that actually reached Earth was negligible and detectable. The comet posed no threat, but the coincidence of the comet's appearance with unrelated events, solar activity, political instability, Earthquakes fueled panic. People connected dots that shouldn't be connected. We are seeing something similar now with Comet By. This By Atlas comet is genuinely strange and unusual. Mercury and Ceres coincidentally appeared simultaneously. And suddenly, people are building stories that perhaps the comet is being awakened by some resonance of the solar system. Perhaps its orbit is being altered subtly by gravitational disturbances. Maybe all this is part of a bigger pattern that we do not yet understand. Astronomers ran the numbers on Mercury's gravitational influence on an object in the outer solar system. Basically none. Mercury is very small, only slightly larger than our moon, and it is very far away. Ceres is even smaller and less influential. The combined gravitational force of all the planets in the solar system cannot significantly alter Bai's orbit at the distances we observe it. The comet is doing what it does because of internal processes, solar radiation, and its own composition, not because of Mercury's position in its orbit. But the truth is not always important when stories are compelling. The human brain craves stories. We want events to be connected because unconnected events feel random, chaotic, and meaningless. If comet activity is linked to planetary positions, then there is order, predictability, and meaning. If they are unrelated, then we live in a universe where strange things sometimes just happen, and that is psychologically unsettling. Confirmation bias amplifies this effect. Once you start looking for connections, you will find them everywhere. Mercury also appeared in a previous comet discovery. Ceres was near opposition position when another unusual object was discovered. No need to worry that Mercury appears several times a year and Ceres reaches opposition annually. No need to worry that unusual astronomical discoveries happen continuously. The brain filters out coincidences and only remembers things that fit the story. Social media exponentially amplifies this. In the past, if you had a theory about planetary alignments affecting a comet, you could tell your friends, who might tell you it was nonsense, and that would be the end of it. Now you post your theory online and immediately find a community who think the same way. You share links, images, charts showing the alignment. AI adds new evidence, others share it further. Soon, you have a complete alternative story competing with the scientific explanation. The lesson here is not that people are stupid or gullible. The lesson is that coincidence is very powerful, and our brains are not well calibrated to statistically dismiss them. With thousands of astronomical events happening all the time, some will coincide perfectly by chance, and those coincidences will feel meaningful even if they are not. This matters, because it affects how people interpret anomalies like Comet Bay. If you are primed to see cosmic conspiracies, to believe alignment is important, then the comet's strange orbit becomes evidence of something bigger. Perhaps it is not a natural comet at all. Maybe it is artificial. Maybe it is responding to signals from planets. Maybe it is part of some grand cosmic mechanism we do not understand. And that brings us to a chapter, even stranger in this story, the machinery of hoaxes, conspiracy theories, and how humans turn scientific mysteries into cultural myths. Part 9, 10/2025 update. Whether this flight actually happened. 8/10/2025. Blue Origin's NSBA-6 mission took place, with 6 passengers on board lasting 11 minutes, and a mysterious passenger whose name was kept secret until the spacecraft landed safely. The capsule was launched, passed the Kármán line, floated in a microgravity environment, descended under a parachute, and landed successfully in the Texas desert, marking another flawless flight for the company's space tourism program and their 15th manned mission. It almost became routine. That was the official story reported by BC News. Medium posted an article, and some space journalists tweeted about it. The mysterious passenger's identity was revealed after landing as an individual who requested to remain anonymous throughout the flight but happily had their name disclosed afterward. And this is completely normal because people are always willing to pay for privacy. But the strange thing was the silence, the almost suffocating lack of news. No live videos, no trending hashtags, no reactions from celebrities, memes, or analyses on TikTok were created, making any AI closely monitoring the aerospace industry feel uneasy. A flight into space, a commercial crew crossing the boundary of space, an event that just a few years ago would have been headline news for days, now, almost, attracted no attention. Think about that for a moment. As humans left the planet, experienced weightlessness, saw the curve of the Earth contrasting with the deep black space background, and returned safely. This is extraordinary. It should be extraordinary. Yet the internet community just shrugged. Social media moved on to other topics within hours, and the story vanished like smoke, prompting questions. Why is there so little documentation about this flight? Blue Origin usually releases cabin footage with beautiful angles of passengers floating, laughing, and pressing their faces against windows. So, where are those images? Why weren't they widely posted on every news site? And why did revealing the mysterious passenger's identity not spark curiosity? Who are they? Why do they want to remain anonymous? These are very natural questions, the kind that usually generate days of speculation and interest. But instead there was absolute silence, as if the flight happened in a vacuum. Not just a vacuum of space, but also a vacuum of public attention. And that vacuum, that absence, begins to feel like a presence itself, making the silence louder than any announcement. You start to wonder and ask uncomfortable questions. Did this flight really happen as described? Were there really 6 passengers, or was the passenger list different? Was the mysterious passenger real, or just a narrative device to explain? The lack of public information before the flight, was the capsule really launched on 8/10, or was the footage just from a previous flight repackaged with a new date stamp? These are paranoid thoughts, like seeing shadows everywhere and trusting nothing. But sometimes the absence of evidence becomes significant, because when something that should make a splash doesn't, you have to ask why. Compare this to 2025, just 6 months earlier. Blue Origin launched another New Shepard mission, and that mission exploded in public consciousness. Not because of a malfunction, but because of who was on board Katy Perry, Gayle King, the first all-female crew, influential passengers with millions of followers. A type of flight designed to make headlines. And it did. But not the headlines Blue Origin wanted. Just hours after the live stream ended, social media exploded with conspiracy theories. People claimed the flight was faked, analyzing every frame of the footage to find inconsistencies in the behavior of hair in zero gravity. It became a forensic battlefield. Does the hair float correctly? Does it move too stiffly? Is it real hair, or a wig, or computer-generated? And the capsule hatch became another focus. Some claimed it opened differently than in previous flights, posting side-by-side comparisons with arrows and circles, pointing out supposedly unusual details. Wasn't the latch on the other side last time? Didn't the door open outward before? Here it looks different. Then came the really crazy claims about green screens, accusing that the passengers were filmed in a studio with fake windows projecting pre-recorded Earth footage, accusations that the hand looks like a mannequin hand, too smooth and artificial, along with complaints about the lack of visible scorch marks on the capsule after re-entry. Every tiny detail became evidence of deception. Journalists systematically debunked the claims, rushing to explain the strange behavior in a microgravity environment due to the absence of gravity pulling it down, so it reacts to electrostatic airflow and random motion. The hatch mechanism is identical across flights, but camera angles and lighting make it look different. Reflections in the windshield distort perspective. Scorch marks are not always visible depending on the dustiness of the location, landing, and camera resolution. But the debunking did not stop the theories. It even fueled them among those wanting to believe the flight was fake. They interpreted the debunking as a cover-up. They dug deeper, seeking more evidence and building complex models on how the hoax was carried out, making the conspiracy theory self-sustaining. Now we have 2 flights, 2 missions, the same type of rocket, the same basic profile, 6 months apart. One flight created a storm of attention and suspicion. The other barely made a sound. And you have to ask which is more suspicious. Part 10. Space mysteries like cosmic mirrors always throw us unexpected curves, mismatched objects, meaningless signals, phenomena that violate our carefully constructed models. And each time we do 2 things without fail. First, we rush to understand the science. Second, we project ourselves onto the mystery. Think about Oumuamua in 2017, the first confirmed interstellar object passing through our solar system. It tumbled, was slightly red, elongated, and accelerating not much but measurably as it left the solar system. That acceleration did not fit an orbit caused purely by gravity. Something was pushing it. Scientists proposed outgassing phenomena. Although no gas was detected, it might be releasing a small amount of volatile material creating thrust like a weak comet. Or it could be an iceberg, frozen hydrogen, H2, sublimating invisibly. Or it could be a fragment of a broken planet with shape and spin creating radiation pressure effects. But a group of people, including some scientists, proposed another idea. What if Oumuamua is an artificial object, a light sail, a solar sail, a thin sheet of material pushed by starlight? That would explain the acceleration. And if artificial, maybe it is a probe from another civilization exploring. Or maybe it is an abandoned object. Space debris from a long-dead alien society. The same thing happened with the star KIC 8462852 in the Kepler field, showing strange dimming patterns, deep and unusual drops in brightness, sometimes dropping by 20% or more. No planet could do that. No planet is large enough to block so much light, and the drops are not regular. Like a planet transit, astronomers propose dust clouds, comet swarms, debris from a planetary collision, but a half-joking paper suggested a gigantic alien structure, a Dyson swarm of millions of solar panels, or a rotating habitat around the star capturing 10% of its energy, which would block light unusually as the structures move. It fits the data somewhat. Strange radio circles, fast radio bursts, By Atlas. Every mystery becomes a screen on which we project our hopes and fears. Are we alone? Is the universe indifferent or purposeful? Are there others out there? And if so, are they like us or unfathomably alien? Psychology is strong here. Pareidolia. The tendency to see patterns and randomness is part of it. We see faces in clouds, hear voices in white noise, and see intelligence in astronomical anomalies. That is not stupidity. That is how our brain works. We are pattern recognition engines, and we tend to favor false positives better to mistake a shadow for a predator than to mistake a predator for a shadow. There is also an existential craving. We want contact. We want to know we are not the only sparks, the sole consciousness in a vast, cold universe. Every anomaly is an opportunity, a possibility, a door that might open to something extraordinary. And so we push those doors, and we push hard. By Atlas is a mirror in its glowing blue halo. In it, we see the reflection of our own curiosity, our desire for meaning, our hope that the universe is stranger and more wonderful than we imagine. And perhaps it is so. Perhaps one day we will find something truly inexplicable, something that forces us to rewrite physics, or accept that we are not alone. But that day has not come yet. Currently, we have an interstellar comet, a strange comet, a fascinating comet, but perhaps just a comet, and that is enough because even natural mysteries are extraordinary. Part 11. Archive of Extraterrestrial Systems. Imagine the galaxy as a library. Not a library of books, but a library of objects, comets, asteroids, rogue planets pushed out during the chaotic formation of planetary systems and launched into interstellar space. Each object is a message in a bottle, carrying information about the star system where it formed, and occasionally, one of those bottles drifts to our shores. That is what interstellar objects are, postcards from extraterrestrial systems. Not extraterrestrial in the sense of intelligence beyond Earth, but extraterrestrial in the sense of being alien. Different. Formed under conditions unlike those in our solar system. Each object we detect is a data point, a unique sample, and with enough samples, we begin to understand the diversity of chemical reactions in planetary systems. Comets in our solar system are relatively homogeneous. They formed in the same protoplanetary disk from the same type of gas and dust well mixed under the same radiation field. Comets have differences. Certainly, some more carbon monoxide, some more water, depending on their formation location in the disk and the temperatures they experienced. But they are members of one family, mostly siblings or relatives. Interstellar comets are strangers. They formed elsewhere under different stars and disks with different compositions, different temperatures, different dynamical environments, and so far every object we have seen is different dry, no outgassing, strange shapes, mysteriously accelerating. It is unlike our comets. It does not behave like our comets. If it is a comet, it is a type we have never encountered. 2I by Borisov, rich in carbon monoxide, is a fairly typical comet but with a gas-to-dust ratio indicating a formation environment, colder than most of our comets. It looks familiar but with subtle differences, like a dialect of the language you speak. Oumuamua ejects water and carbon dioxide at very large distances. Nickel without iron appears late. Nothing about its behavior matches our experience. It is speaking a language we barely recognize. Different objects, wildly different chemical reactions. If we extrapolate, if we assume this object represents a larger population, then the diversity of comet compositions in the galaxy is astonishing. Not all planetary systems create comets like ours. In fact, probably most do not. Think about the implications in some systems. Comets may be dominated by nitrogen ice, like the surface of Pluto. In other systems, methane may be the main volatile. In systems with larger stars, the snow line, the distance where water ice can condense, will be farther out. So, comets can form in colder regions and carry different mixtures of volatiles. In systems with giant gas planets, the disk will be stirred, mixing materials from regions of different temperatures, creating comets with strange hybrid compositions. Some comets may carry molecules we have never seen before, molecules that are thermodynamically possible but require formation pathways that do not exist in our solar system. Exotic organics, strange ices, compounds that might make a chemist's eyes light up. Perhaps the universe is very large. The parameter space of comet mass, disk composition, radiation field, and dynamical environment is vast. Naturally, exploring that parameter space thoroughly, and some results must be strange. Now, take this one step further. If life requires certain chemical building blocks, water, organics, phosphorus, nitrogen, sulfur, then comets lacking those components will be sterile. They cannot seed life. They cannot provide prebiotic chemistry, nitrogen and sulfur. So, comets lacking those components are sterile. They cannot seed life. They cannot provide prebiotic chemical reactions. For planets, perhaps many interstellar comets are sterile. Maybe Oumuamua is a lifeless rock tumbling through space. But if even a small fraction of comets carry the right chemistry, that small fraction is important because comets are galactic wanderers. They travel between stars, crossing light years, and if they carry organic molecules, amino acids, maybe even viruses, inactive, shielded deep inside, then the building blocks of life could spread throughout the galaxy. This is the panspermia theory. The hypothesis that life can be transferred between worlds on comets or asteroids is controversial and unproven, but it is not impossible. And By Atlas, with its water and organic cyanide compounds, has components that may not be life, but are chemical reactions that could lead to life. If delivered to a suitable planet, every interstellar object we detect expands our sample. Right now, we have Ba in 15. We could have 10s and 5500s, and with each object we will measure composition, orbit, and activity patterns. We will build a statistical understanding of what exists out there. Perhaps we will find that water-rich comets are common, that most planetary systems produce them, or perhaps we will find that our solar system is unusual, that water-rich comets are rare, and most systems produce dry, oily, carbon-rich objects. Both answers are intriguing, and perhaps we will find a comet with clear biosignatures, molecules that are hard to explain without biology, phospholipids, complex organic compounds with symmetry, isotope ratios indicating metabolism. That would be revolutionary. That would tell us life arose elsewhere, that biochemistry is not unique to Earth. We have not found that yet. By Atlas does not carry life as far as we know, but it carries information. And information is the currency of science. Every visitor to a star is a gift, a free sample delivered to our doorstep. All we have to do is look closely enough. Part 12. Nico is a messenger. Let's return to Nico's anomaly because it is not just a curiosity. It is a clue, a chemical fingerprint, and fingerprints tell you where someone has been. Stars are nuclear factories in their cores, taking hydrogen and helium to build heavier elements like carbon, nitrogen, oxygen, silicon, sulfur, iron, and when massive stars explode as supernova, the explosion creates even heavier elements including calcium, These elements are dispersed into space, mixed into gas clouds, and eventually incorporated into new stars and planets. But not all stars have the same recipe, the abundance of heavy elements. What astronomers call metallicity varies. Young stars formed recently from gas, enriched by many generations of supernovae, have high metallicity. Old stars formed when the galaxy was young and fewer. Supernovae occur, have low metallicity. Nickel and iron are both produced in supernova, but in slightly different amounts depending on the type of supernova explosion. Type Ia, where a white dwarf accumulates matter and explodes, producing a nickel to iron ratio different from core collapse supernovae, where a massive star collapses. If BAE Atlas formed in a system whose birth gas cloud was enriched by an unusual mix of supernovae, its nickel to iron ratio could be skewed. Now we think BAE Atlas may come from the thick disk, an older star population. Thick disk stars have overall lower metallicity, but the ratios of heavy elements vary. If the nickel separation we see in BAE Atlas reflects the composition of its parent star, then that comet is a tracer, telling us about galactic chemical evolution in ways not easily accessible. Because this is important, we can analyze stellar atmospheres by spectroscopy. We can measure their iron, their nickel, and everything. But stars are very far away. We can only study a very small fraction of them in detail, and we cannot study stars that no longer exist, stars that lived and died billions of years ago. But comets from those systems are their time capsules. They preserve the chemical conditions when they were born. If we can sample BAE Atlas directly, analyze its isotopes, elements, quantities, its mineral structures, we will hold in our hands a piece of a star system possibly billions of years old and thousands of light years away. We will read history written in atoms. Now consider a speculative idea. A fringe idea, but one discussed. In certain groups, could the abnormality of metals like high nickel be a sign of processed material? Not naturally processed like thermal metamorphism, but technologically processed. If an advanced civilization is mining asteroids and refining metals, building structures in space, they would produce waste, debris, exhaust. That material would have unusual elemental ratios because industrial processes are selective. For example, you extract iron to build something and discard nickel residue. Or you use nickel in a specific application and throw away everything else. If a comet forms in a debris disk containing industrial waste, it could incorporate those unusual metals, and then millions or billions of years later, that comet is ejected to wander the galaxy and arrives in our solar system. We detect the nickel anomaly and scratch our heads to be completely clear. There is no evidence showing Bailey's is artificial or contaminated by technological signatures. Nothing. This idea is speculative to the point of science fiction. Most scientists reject it immediately. But it is not physically impossible. And when there is no clear natural explanation for the nickel isotope anomaly, even Dinso's ideas are listened to. A more reasonable explanation is a mundane chemical reaction of nickel in organic compounds, fractionation during condensation. Some process we have not thought of operating under common conditions in other star systems, but rare or absent in ours. But this is what excites me. Every comet carries a chemical signature, a barcode written in elements and isotopes. If we build a library of those signatures, if we catalog the composition of tens or hundreds of interstellar objects, we can start mapping the galaxy. We can correlate chemical signatures with orbits a comet coming from the galactic center direction. Might have a different abundance than a comet from the outer halo. A comet from a thick disk might show age-related signatures. We can use comets as tracers of galactic structure and evolution. Imagine a future where interstellar objects become common, where our detection technology is so good that we catalog tens each year, each object properly analyzed. The orbit of each object traced back as far as possible, the composition of each added to a database, and eventually patterns will emerge. We see that comets from one region of the galaxy are carbon-rich systematically. Comets from another region are water-rich, and we start to understand why. Perhaps carbon-rich regions form many low-mass stars, have different planetary disk chemistry. Perhaps water-rich regions have more supernova activity, enriching the gas with oxygen. BA Elias is the start of that library. One entry, one data point, but it is a start. And the strange nickel isotope anomaly is a reminder that every data point has a story. Every elemental ratio is a clue. And if we are patient, if we are careful, we can read those stories and piece together the history of the galaxy itself. Part 13. Invisible Population BA Objects. Oumuamua 2, Borisov BA, and Atlas BA confirmed interstellar visitors over 7 years. That's not many, but enough to do statistics, enough to estimate how many other objects are out there passing by undetected. Astronomers have run the numbers based on detection rates, survey coverage, and observed properties of these objects. They estimate that at any time there are probably several interstellar objects inside Jupiter's orbit. Small, dark, fast-moving, invisible to most telescopes. We detected Baileys because we were lucky they passed near Earth, were bright enough, or in the right part of the sky when the right telescope was observing. How many do we miss? Hundreds, thousands, for every interstellar comet we detect. Maybe tens pass unnoticed. Some are too dim. Some move too fast to track. Some appear in parts of the sky we don't monitor. Detection is very difficult, but becoming easier. New surveys are being deployed with unprecedented sensitivity and sky coverage. The Vera Rubin Observatory currently being built in Chile will scan the entire visible sky every few nights. Photographing everything down to extremely faint magnitudes, it will detect asteroids, comets, supernovae, anything that moves or changes, and it will find interstellar objects. Estimates suggest Rubin could detect 1 interstellar object per month, perhaps more, at least 12 per year. In 10 decades, we will have over 100 confirmed interstellar visitors, which is a sufficient sample to start drawing practical conclusions about their composition, the origin of the population, the Square Kilometre Telescope Array, SKA, a radio telescope network being built in Australia and South Africa, and will also contribute radio observations capable of detecting molecular emissions from comets, even faint comets. SKA can detect interstellar comets that optical telescopes miss. Ultraviolet and infrared space telescopes will catch active comets, but obscured at optical wavelengths. Every new instrument expands our detection capabilities. The ability to see these faint, fast-moving, wandering objects, but detection is one thing. Research is another. Interstellar objects moving fast, tens of kms per second relative to the Sun. So, by the time we detect them, analyze their orbits, and plan follow-up observations, they have usually already left. Oumuamua is on its way out of the solar system. When we detected it, we only had time to see it clearly once before it faded into too much empty space to observe. To Borisov we caught while it was inbound. This gave us months to study it. Telescopes worldwide focused on it. We obtained spectra, light curves, detailed observations. That was the ideal scenario. By Atlas. We also caught it relatively early. We are receiving good data, but soon it will reach perihelion around the Sun and return to darkness. And then it will disappear forever unless we intercept it. There are proposals for intercept missions to interstellar objects. Spacecraft designed for rapid launch and strong acceleration. To meet an interstellar visitor while it is still in the solar system, the technical challenges are huge. You will need a spacecraft on standby, ready to launch on short notice. You will need powerful propulsion systems to match the object's velocity and instruments capable of analyzing composition, structure, possibly even collecting 10 samples. But the rewards would be extraordinary. Imagine landing on an interstellar comet, drilling into its surface, collecting ice and rock samples from another star system, bringing them back to Earth for laboratory analysis. The science we could do with that material is almost unimaginable. We could determine precise isotope ratios to learn about nuclear processes in the parent star. We could analyze complex organic molecules in ways you cannot do remotely. We could search for amino acids for prebiotic chemical reactions, possibly even fossil microbes, if we are extremely lucky. Even if we do not find life, we will know about chemical reactions in exoplanetary systems, in detailed, subtle ways. Every molecule, every mineral, every isotope will be a clue. Some scientists have planned such missions. Concepts have existed. Budgets are proposed. This is not science fiction. It is engineering. Difficult engineering, but feasible. In 55, perhaps 100 years. We may have cataloged hundreds of interstellar objects. We may have intercepted a dozen. We may have brought back samples from half a dozen, and with that data, we will have a comprehensive understanding of the galactic comet population. the diversity of planetary systems, possibly even the prevalence of the building blocks of life in the galaxy. By Atlas is a preview, a glimpse of what is possible. It shows us that interstellar comets are not just rare curiosities. They are common, they are everywhere, and they carry the information we crave. The invisible population is out there tumbling in the dark, waiting for us to find them. And we will do so one by one. We will catalog them, study them, and piece together the puzzle of how planetary systems form, how chemistry varies across the galaxy, and perhaps, just perhaps, how common life really is. Part 14. When anomalies in matter zoom out. Look at the bigger picture, because By Atlas is not the only strange thing happening in astronomy today. Not at all. Strange radio circles, mysterious radio emission rings of unknown origin, fast radio bursts, millisecond radio energy pulses from distant galaxies, mechanisms under debate. Tabby's star, strange, unexplained dimming patterns, Oumuamua, an interstellar object with unusual acceleration. By Atlas, comets with impossible water production and metal anomalies. And those are just the prominent cases. There are perhaps dozens, maybe hundreds of lesser-known anomalies. Transient events do not fit known categories. Spectral features should not exist, moving objects in ways that challenge. The easy explanation astronomy is witnessing meaningless things, and that is new. Most of the 20th century astronomy lacked data. You point a telescope at an object, take photos or spectra and spend months analyzing it. Discoveries are rare. Anomalies even rarer. When something strange appears, it is scrutinized closely because not much else competes for attention. Now we are drowning in data. Automated surveys generate terabytes every night. Sky surveys catalog billions of objects. Gravitational wave detectors, record mergers, radio telescopes scan the sky continuously. We are detecting more than we can track, and with large numbers comes a high anomaly rate. If you look at a billion objects, even if only 1 in a million is strange, that is 1,000 anomalies, most will turn out to be instrument artifacts. Data glitches, misclassification. But some will be real, and screening them takes time. We are in an era where anomalies outpace theory. We are finding things faster than we can explain them, and that is both exciting and dangerous exciting, because new phenomena drive new physics. The discovery of R process bursts, gamma ray, bursts, gravitational waves, all started with unexplained observations. Anomalies are where breakthroughs happen, but dangerous because hype cycles can get out of control. Every anomaly is hyped as potentially revolutionary. Megastructures, aliens, signs of warp drives, wormholes, dark matter, interactions. Favorite stories, the public loves that. And then 9 times out of 10, the anomaly is explained by something mundane. Dust clouds, instrument noise. Known. Objects misidentified. The risk is erosion of credibility. People hear aliens a dozen times, and the reality is just dust a dozen times, and they stop trusting scientists. They start thinking science is wild speculation. Or worse, they double down on alien explanations. Decide scientists are covering something up. The Tabby's star story is a cautionary tale. When the megastructure alien hypothesis hit headlines, the public latched on, social media exploded. Articles reported it, and when follow-up observations showed wavelength-dependent dimming indicating dust, not solid structures, there was backlash. Some accepted the explanation. Others insisted scientists were wrong or lying. But here's the important thing. Tabby's star remains interesting. The dust explanation does not fully explain all observations. Long-term monitoring shows complex variability. It is a strange star, possibly surrounded by a debris disk from a planetary collision. It may be something we do not fully understand yet. It is still science, still valuable, just not aliens. The lesson is anomalies are opportunities. They push us to refine models. Consider new mechanisms, challenge assumptions. Even if they don't revolutionize physics, they still drive it. Oumuamua's acceleration, even if just outgassing, forced comet scientists to rethink low-temperature sublimation, exotic ice's surface properties. That is progress, BAE. Atlas is another opportunity. Its water production challenges our understanding of volatile activation. Distances, its nickel anomaly forces us to think. about metal chemistry in comets something we largely ignored because our comets don't show strong metal emissions. Its carbon dioxide dominance raises questions about protoplanetary disk conditions in other systems. When you pile on enough anomalies, patterns may emerge. Perhaps strange radio circles and fast radio bursts are related. Both involve flows of energy from galactic centers. Perhaps interstellar objects like Oumuamua and BAE Atlas represent distinct populations with different formation mechanisms. Perhaps the transient zoo of astronomical phenomena is telling us something fundamental about the universe's robustness. Or maybe not. Maybe they are all unrelated individual quirks happening within the same few decades, because finally we have the technology to detect them. Both answers are informative. The key is maintaining skepticism and wonder. At the same time, you can be excited about an anomaly without claiming it rewrites physics, can investigate strange possibilities without being tied to them. You can change your mind when new evidence arrives. This is where good scientific communication becomes important. When reporting on Comet Atlas, journalists and scientists have a responsibility to say, "This comet is behaving unusually. We are investigating several possible explanations. This is what we know so far. It is not an alien comet violating the laws of physics. Scientists are not confused by an impossible object. But subtlety does not generate clicks. Careful wording does not go viral. And so the hype machine still works, turning every anomaly into a potential revolution, causing disappointment. When mundane explanations emerge, the solution is not to stop reporting anomalies. The solution is honesty about uncertainty, presenting multiple hypotheses, updating as evidence changes. Treat the public like adults who can handle ambiguity, because most people understand that science is a process, that answers evolve, that not knowing is a perfectly acceptable response. Comet Atlas is an anomaly in a stack. It is important. It is fascinating, but it is not proof of anything. It is a data point, a mystery, an opportunity to learn, and whether it ultimately is a strange natural comet or something we have never seen before. The process of studying it, testing hypotheses, ruling out explanations is valuable. That process is science, and science, when done honestly, is one of humanity's greatest achievements, even when, especially when it struggles with things it does not yet understand. Part 15. Final reflections. So, here we are. Thousands of words deep into the mystery of Comet Atlas. A comet spilling water into space, where water should not flow, glowing blue with nickel and cyanide, flickering on and off like something intentional, carrying chemical reactions from another star system, possibly another era of galactic history.